Hello general chemistry students, this is the third video in week 12, and in this video we're going to be talking about solving problems using ice tables and finding equilibrium concentrations. So by the end of this video you will be able to calculate equilibrium concentrations and also use those ice tables that we'll talk about to solve equilibrium problems. All right, so let's talk a little bit about those heterogeneous equilibria. So what I mean by that is that a mixture that is heterogeneous, for instance, you might have a liquid and a solid together that aren't soluble in each other. So when we write these equilibrium expressions, pure solids and pure liquids do not appear in the equilibrium expression. And the reason that is because the amount, even though the amount can change, the amount in solution is not going to change because it isn't in solution. All right, so because their concentration doesn't change, solids and liquids will not be included. All right, so imagine we have this reaction. So we have A plus B going to C plus D. In this reaction, we have A as a solid and we have C as a liquid. We're not going to include those in the equilibrium expression, so we'll just use D and B because they are aqueous. So D to the D power divided by B to the B power. That's the equilibrium expression for this reaction. All right, so in this reaction we have CO gas forms CO2 gas and carbon solid. Okay, so we need to think about how to write an expression for this. So the amount of carbon is different, but the amount of CO and CO2 remain the same. So therefore, the amount of carbon has no effect on the position of the equilibrium. So we're not going to include carbon in our equilibrium expression. So if we're going to write this in terms of either Kc or Kp, we'll take the concentration of CO2 over the concentration of CO squared and not include carbon solid. All right, so let's look at these reactions and write their equilibrium expressions. And of course, because we know the K, we can predict the position of the equilibrium. All right, so for Kc here, we have H3O plus times nitrite divided by HNO2. We're not including water here. We're not including water because it's a liquid and the concentration isn't going to change much here. And if we look at the value of K, we can see that it is small, therefore it favors reactants. Right, so let's look at the bottom reaction. Here we have a precipitation reaction, but in our K expression, we're not going to include that solid. So we just have HNO3 squared divided by calcium nitrate times sulfuric acid. If we look at this reaction, we see we have a very large K, therefore it favors products. Right, so it's important to remember when we're writing these equilibrium expressions not to include pure liquids like our water and not to include solids like our calcium sulfate. All right, so what we're going to do in the next few slides is we're going to calculate equilibrium constants by measuring the equilibrium concentrations. So we've let this reaction go to equilibrium and we're going to measure those concentrations. And so from this, we can find the equilibrium constant as long as the temperature is constant and the equilibrium constant is independent of the individual amounts of reactants in product. Okay, so let's look at this reaction. So we have H2 plus I2 goes to 2HI. Right, so we have our initial concentrations, we have our equilibrium concentrations, and we can calculate the equilibrium constant. Okay, so here we're going to keep we're going to keep the temperature the same at all of these reactions, and we're going to calculate the value of the equilibrium constant. All right, so what you can see here is over and over my equilibrium concentrations, calculated equilibrium constant, that's the same. So what we can say here is that that equilibrium constant is independent of the concentrations of the reaction. Okay, so if you're doing a reaction that's very highly concentrated or a reaction that's not very highly concentrated, the equilibrium constant is going to be the same, provided that you're at the same temperature. All right, so let's go forward with calculating equilibrium concentrations. So the stoichiometry is very important here. It's going to help us determine the equilibrium concentrations of the reactants. If you know the initial concentrations of at least one of the equilibrium concentrations. Okay? So we're going to use that change of the concentration to determine what those equilibrium concentrations are. All right, so here's an example. We have this reaction of 2A plus B going to 4C. We have our initial concentrations of A and B and C. Of course, the product is 0. And when we reach equilibrium, we see that we have a concentration of 0.5 molar for C. So our product now is 0.5 molar. Notice this is stoichiometry. 2A plus 1B goes to 4C. So that's really important when we calculate the equilibrium concentrations. All right, so we're going to look at what we're going to call an ice table. So an ice table really is initial change in equilibrium. Okay, so we set up a table where we show all of our reactants and products. So we're showing our A, our B, and our C. And really this table is used to keep track of concentrations. So we're going to first put in our initial concentration because those are given. We know that we have 1 molar of A, 1 molar of B, and nothing for C because it's a product. And we also know that at equilibrium we have 0.5 molar of C. Okay, so we can set up the ice table first off with the things that we know from the problem. All right, so we know that the product has increased by 0.5 moles per liter. All right, and because of stoichiometry, you must have 1/4 that amount of reactant B because it's 4 to 1 according to stoichiometry. All right, so then we can say that we have 0.125 molar of B. All right, so then let's look at C. So if we have 0.5 molar of C and it's a 2 to 4 ratio, that means we'll end up with 0.25 moles of A. Okay, so what we've done here is we've taken our initial, subtracted the change, and we came up with 0.75 for A. And in this case, we took our initial, subtracted our change, and ended up with 0.88 of B. And here we've taken our initial, add in what the change is, and we add in, and we knew that we had 0.5 molar to start with. Okay, so here we use stoichiometry to determine what those changes were so that we could take the initial minus the change and come up with the equilibrium concentrations. So now we have enough information to calculate an equilibrium constant. All right, so here we're going to find the value of Kc for this reaction. So we have an initial concentration of a reactant, methane, and we have an equilibrium concentration of our product. Okay, so we have enough information to set up an ice table. Remember It's initial change equilibrium. So the first thing we're going to do is we're going to put in what we know. And what we know is that we have an initial concentration of 0.115 molar for the methane and an equilibrium concentration of 0.035. Okay, so now we have to use stoichiometry to determine what that change is. All right, so we know that we're going to product, we changed by 0.035, and so we're going to use that information, use stoichiometry to determine how much of each thing changes. How much does the hydrogen change? How much does the methane change? All right, and so from stoichiometry, we know that for every one acetylene we produce, we use 2 moles of methane. Okay, so that's where that 2 comes from. And also notice it's a -2 because it's a reactant and the reactant goes away in time. So -2. All right, so but what about the hydrogen? Well, the hydrogen, for every 1 C2H2 we form 3 H2. So we'll multiply times +3. Okay, so now what we can do is we can take our initial and for the reactant subtract out the change, and we end up with 0.045. And then we're going to take our 3 times 0.035 to come up with 0.105. So now we have all of the equilibrium concentrations in this reaction. And then we can go further and calculate the equilibrium constant. So first let's set up the equilibrium expression. So we have our products, so C2H2 times H2 cubed divided by our reactants, CH4, and we're going to square that. Okay, so we take those concentrations. So we have 0.035 times 0.105 cubed divided by 0.045 squared. And this is our equilibrium constant. All right, so let's look at this reaction, and we're going to complete the table and determine the values of Kp and Kc. All right, so we know, so we have NO2 forming N2O4, and we know that we have an equilibrium concentration of our NO2, and so we calculate that change. And by stoichiometry, we know that for every 2 NO2s, we form 1 N2O4. And so we can calculate our equilibrium concentrations. Okay, so this is multi-step. So first we're solving for Kc, and then we're going to convert to Kp. So Kc here is 0.0014 divided by 0.0172 squared. All right, that's our Kc expression, and we get 4.7. Okay, so now what we're going to do is we're going to need to convert Kc to Kp given our RT delta N. Okay, so let's look at delta N. We have 1 gas molecule, and we have 1 gas molecule in the product and 2 in the reactant. So again, we have our -1 delta N. All right, so we take our R times our T because it's 100 degrees, raise it to a -1, and multiply times our Kc, and we get 0.15. Right, so we have done a few things here. We've kind of just put this all together. We've calculated the change in concentrations so that we could come up with equilibrium concentrations. We've calculated Kc by knowing our equilibrium concentrations, and then we've converted Kc to Kp because they're gases once we knew what Kc was.